Very good morning. We are going to learn the course entitled Computational and Numerical Methods, which requires some concepts from calculus and linear algebra, such as mean value theorem, Taylor series, how to solve system of linear equations, and so on. How they are going to used as fundamental tools to derive numerical methods and techniques for attempting or for solving solutions we are going to learn in this course. Yeah. Okay. So we here let's here so therefore the objective of this course is to understand or learn various numerical methods for solving mathematical problems, of course by using a computer. Further, we are going to see the error analysis part, which is going to be the very uh, uh, most focused part in our course, that we should be able to achieve the desired accuracy of the our to the solution of the problem. Okay, right. Other important thing, what other objective is to on student skills in computer programming and program solving. Right. Okay. So with these objectives, we will move further in this course. Yeah. So the team is Dr. Madhukan Sharma. We are going to uh, I will be delivering all the main lectures, and the lab session will be supervised by Miss Janvi Chauhan. She will be there for you for clarifying your doubts and in their problem sheet. And of course, sometime it's like based on the requirement, I will be also present there. Right. Okay. So the very other important aspect of this course is the marking scheme or evaluation part. So there will be one mid-semester exam and semester another end semester exam, and so they will contribute respectively 25% and 45% of the marks, right? And other components, such as there will be an exam based on your lab. There will be one project will be given, and some assignment part will be there, so that these three part of course together will contribute to 30% of your evaluation part. Okay, right. So these are the reference books. So the first very I should mention here the what the which book I am going to follow as a textbook by this by Kincaid and Cheney, that is Numerical Analysis and Mathematics of Scientific Computing. It is a American Mathematical Society book. Right. Okay. Other reference books are like by Conte and Poor, and by Atkinson, Borden and Douglas, and Jane and Younger. The very famous book, Douglas and Borden and Jane and Younger. Of course, some of the part we are also going to take from the Conte and Poor. Okay. So, without any further delay, let's move to our the content of the course. This course, okay, and start learning our things. Okay, so I will try to recall the basic fundamental concepts in whenever they need to be. However, you are suggested here to revise your concepts and be comfortable with them. Right. Okay. Uh, so the very first thing is that because you are going to work with a computer, so this is means you need to understand the how the integers or fraction number are represented within a machine. So the normalized scientific notation, so here with the base beta, Okay, so beta could be any greater than one number. Okay, so in fact, in available computer machines, they are accepting the input you will give in decimal number. Machine will convert into binary number, and then it will give it will the and output will also come in terms of decimal number. So there is some conversion going on, and was and then during that process there will be some error analysis will be also taken part, that we will try to understand uh, here itself will how they occurs. Okay, so that normalized scientific notation is as follows: if you take any non-zero real number, then it can be written as x equals to either positive or negative, and you can always write a number like this: point b1 b2 b3 with base beta into beta to power e. So for example, you have you have here uh, uh, you can always write like I have a number 2 4 243, and this is with the, let's say, 243.123. So one real number with base, let's say, 10. Okay, so we actually we are not writing with this braces with base 10. We can always write in this normalized scientific notation form by just writing at 0.243123 time time 10 to the power 3, right? 10 to the power 3. Okay, so with this 10, and this e is here exponent, that is called exponent, and this here, this part is called mantissa. Okay, and this bi's values, if you see these values here, okay, these values are, all the values are lying between the set 0 comma 1 2 3 and so on with 9. So if you wish to represent with the any base beta, okay, so then here bi is, what is expecting is, what is bi is, bi should be in the set, so these bi's must be in the set 0, sorry, uh, bi must be in the set 0 1 2 and so on beta minus 1. As I mentioned, this part is called the mantissa, and e is called the exponent, right? Okay, so yeah, every number can be written as a normalized scientific notation in the form. Okay, so right now the next, I mean, so how the machine converts, means how the machine convert a positive integer to a with any base, other base beta. Okay, so or with any base beta, if you have a number, how it will convert to a decimal number. So that's very famous algorithm is Horner's algorithm. So which actually the statement is very clear that this algorithm converts a positive integer with base beta to decimal. So what is here is, let's p of x is an this a polynomial, the following polynomial of degree n, where this each ei, where each ais are real numbers. Okay, and if you replace x by beta, you will actually these ais are belongs to, yes, this px is only polynomial, these are the real numbers. Of course, if you replace x by beta, ais must be belongs to the set 0 to beta minus 1, and then if you represent this, if you replace this, so what I mean here is, this is this if I replace x by beta, so what it will give me is like p of beta will give you the decimal number. So where these AIs are real number. In this case, what we are mean is AIs are real number belonging to the set 0, 1, 2, and so on, beta minus 1. Okay, so this, if you replace the p of beta, will give you the corresponding decimal integer, right? So converts a positive integer. So this algorithm converts a positive integer, so any positive integer with base beta to decimal. So for example, I have this let's say here 1 1, it's not a comma. Okay, let's just strike it. Okay, so let's see this 1 1 0 1 with base 2. So if I wish to find out in decimal form, that is right, this is here 1 is a naught plus 0 into 2 plus this is 1 into 2 square plus 1 into 2 cube. So that is equals to this is 8 plus 4 12 plus 1, that's a 13 in decimal. So this is what I was trying to explain you, that if you replace x by beta here and AIs are belongs to the set 0 to beta minus 1, it actually gives you it will actually converts a positive integer with base beta to a decimal number. Okay, so what is so I just now what is there is yeah, so I can now work with this polynomial in a, so how to do that? I will use the nested multiplication. So I will write this a naught plus x time, I can write this a1 plus a2x plus a3x square plus and so on, plus and so on, plus a n x to the power n minus 1, right? Now this is equals to a naught plus x time a1 plus x time a2 plus a3x plus and so on, plus an x to the power n minus 2 and so on. So what you will get is at the end here x time an minus 1 plus x time an, and then you have this is here, this in the here, if you keep on doing this process. So first you will get this, then you will get this number, then you will get this sum 2, then you multiply by x and so on. So we have to derive the sequence of that numbers point b1 b2 b3 and so on. How? So what is there is, let's say here how will you derive is as follows. Now this will give you that the following, this will give you the following now. Okay, so generate recursively the sequence bn to b naught. So that's, as I told, that's bn is equals to an, bn is equals to an, then you multi, so what is the bn minus 1 is an time beta and plus an minus 1. So if you recall, this is if you replace bn by an and beta by x, actually you are going to get the same. Similarly for bn minus 2 is equals to, now you once you got bn an, so bn minus 1 is going to use bn, that is beta time bn. Okay, that bn minus 1 equals to an minus 1 plus beta time bn. Similarly bn minus 2 equals to an minus 2 plus beta time bn minus 1 and so on. So that is the final is b naught equals to a naught plus beta time b1, which is equals to p of beta. Okay, so So if I recall, what is here is happening is, uh, this is p of x is equals to, you have to just write this a naught plus x times a1 plus x times a2 plus x times a3 plus and so on, plus x times an minus 1 plus x times an, and these many braces and final braces here. So you are starting with this by doing this an is equal, this you are doing this replacing an by bn, then you're replacing this one an minus 1 plus beta time bn, this one here, and an is here. Then what after that, you are taking this bn minus 1 multiplying by beta, means this is complete this number, and then plus an minus 2. So this is here is an minus 2 here plus, so this is going to be this, and so on. Okay, then finally a naught plus beta time b1, which will give you p of beta. So this will actually converts a positive integer with base beta to a decimal one. Okay, right, fine. uh, yeah, and then next is how to convert a fraction part, means like scientific notation, like if you have a number between an open interval 0 1 and an integer beta greater than 1. So let's take that you have to generate recursively. So I wish to find out any number x belongs to 0 to 1, and I wish to write in the scientific notation, means like you have x is equals to, you have x is equals to some plus, so plus it is because positive number 0 point b1 b2 b3 and so on with base beta. I wish to find out with base beta. Okay, so it's a conversion of a decimal number. Okay, and we are trying to represent with respect to any other base beta. So we are generate recursive. So we are just starting with c naught equals to x. Okay, with starting with c naught equals to x here, and then you are going to I'm going to write b1 is equals to beta time, you multiply this by beta and take the integer part, and then you have c1 is equals to its fraction part. So you multiply c naught by beta, so whatever you are calling, whatever you are getting the integer part, you are storing into b1, and whatever you're going to get in a fraction number part, you're going to get in c1. So I hope you get it now. So b2 is uh, you multiply c1 by beta and take its integer integer part, and then c2 is equals to beta times c1 its fraction part, and so on. Then you will replace then you will get the fraction part number, right? Okay, so this is how you will get this b1 b2 b3 and so on in the when you conversing a fraction part to with any other base beta. Okay, so this is how this is going to be given by this. Okay, right. Now this is very important to understand what are the significant digits in your numbers. So the very first important digits are non-zero digits. They will always be, they are always significant. If you see any non-zero digit in the number, they are always significant. What about zero digits? So if zeros placed before other digits are not significant, what does it mean? zeros placed before other digits are not significant. I mean, for example, you have uh, uh, let's say for example you have here 0 to 4. So we are, is here is we are trying to tell is other means integers in the zeros placed before means other digits are not significant. This means here I think the statement what I mean here is if you have starting with 0 any number, okay, that will not be, they are not the zeros placed, those zeros are not significant. Okay. And what other zeros, so what zeros are significant? So zeros placed between other digits are always significant. So instead of, let's say you have uh, this one, let's consider the example again. So let's see, we have taken 0 to 4 and 204. So here 0 is significant, here 0 is not significant. Okay, so 0, but if you talk about the fractional part means like with decimal number, so 0 placed after other digits but behind a decimal points are significant. So if you have like 24.031, okay, and here also 0, so here all the numbers are significant now. Okay, this 0 is also significant, this 0 is also significant. Okay, so these zeros are placed this means this is how you will decide the what are the significant digits in the given machine number. Okay. Okay, right. So now let's talk about so floating point representation with finite precision. So it's, see, machine will not give means like a number which is not ending, means like with the decimal part point b1 b2 b3 like 1 by 3. So you have in 1 by 3 you have 0.33333 and so on. So you have to either round off or you have to chop, right? So what you will do with finite precision, so how the machine behave accordingly. Okay, so you have the number, so then if you opt for rounding, then what will be the floating point representation? So that depends on your the where you are ending, where you are going to ending with the this series of this b1 b2 b3 and so on, means like suppose you are ending with n plus 1th one. Okay, so now based on the based on this here bn plus 1 that bn plus 1, so you are have point b1 b2 and so on, that bn and bn plus 1. Now depend on the behavior of bn plus 1, it will decide whether you are remaining with bn or you are remaining 1 unit more than bn. So that's what, and that's so on. So you want to stop here. Okay, so the when bn plus 1, so when bn plus 1 is, of course we are talking about greater than and or equal to 0, and if it is less than beta by 2, what is beta here is the base. Okay, so if it is strictly less than means beta by 2, then you will not do anything with bn and you are straightforward at it, that will be giving you floating point representation of the number. However, if bn plus 1 is greater than equals to beta by 2, and it's of course less than beta, because bi's are numbers with like between 0 to beta minus 1. So then you are make one more unit to bn. So instead of bn, you are going to replace it by bn plus 1. So of course, see, when you do this type of rounding, it will lead some type of errors. So there are two type of errors we can talk about. One is absolute error, another is relative error. So now if you see carefully, and if I say if I say this is, let's say this is x minus, and let's say this is for x plus, why I've told this x minus and x plus here, because this is x number, so this if I want to write relation with the x, these x this here. So it should be very clear that x minus is less than equals to x less than equals to x plus. So what it tells you that x minus is sitting on the left of x and x plus is sitting on the right of x, right? Okay, so I wish to decide, this is a approximate number, means either this or that. So this will be, let's say this is x star, approximate number. Okay, so I wish to evaluate the error. So exact value minus approximate value. So it will be always less than equals to 1 by 2 times mod of x plus minus x. Right, it will be always half of the, because approximate number either x minus or x plus, but it will always be less than equals to the length of the interval is means half of the length of the int, because x is either sitting nearer to x minus or sitting x nearer to x plus. It will not okay, so now you can carefully find out what this difference magnitude. Okay, so if you try to find out the difference of this magnitude, so x plus minus x minus, so here it's very clear, this y1 we cancel, b2 cancel, and so on. Here you will have 0.000001. Okay, so that is beta to the power minus n. So if I am not wrong, this is going to be 1 by 2 times beta to the power e minus n, right? That 0.5 times beta to the power e minus n. So this is giving you absolute error. Now this is a absolute error. Okay, this is, we are talking about absolute error. Okay, so this is what we got for absolute error. Okay, now for relative error, what you will do is, so this is what the absolute error. So for relative error, you are going to divide both side by mod x. Okay, so for relative error, what you are going to do is you are going to divide both side by mod x, the length of x. Okay, so what is mod x here is this plus minus point p1, and the mod is always plus, so mod x is equals to right, this is going to be point b1 b2 and so on with base beta time beta to the power e. So beta to the power e will get cancelled. Okay, so what you get is 0.5 times beta to the power minus n divided by point b1 b2 and so on with base beta, this number. Now what can I tell about this? So this I can write this as this number, since b1 is non-zero, since b1 is non-zero, since b1 is non-zero, so I can write this as, so I can write this bracket 1 is as b1 point b2 b3 and so on, okay, with base beta. Right, now what can I tell about this? b1 is non-zero, so means what? b1 is non-zero means what? 1 less than equals to b1 less than beta, right? What it tells you, 1 by b1 is less than equals to 1, right? 1 by b1 is less than equals to, so I can write this as into beta to the power minus 1. So 1 by b1 is less than equals to 1. Okay, so this will imply, okay, this will imply 1 by b1 is less than equals to 1. Now what you will do now, so what about b1 point b2 b3 and so on? What about this b1 point b2 b3 and so on? Yeah. Yeah. What about this point b1 point b2 b3 and so on? So yeah, so what I can do is, see, b1 is less than equals to b1 point b2 b3 and so on. So this uh, sorry, okay. So what this implies is this one here, let me this one here, let's remove it. Okay, I shall okay, yeah, fine. uh, yeah, so if I look at this carefully, okay, if I look at this carefully, and if I try to see, I know this is b1 is less than equals to b1 point b2 b3 and so on. So 1 upon b1 point b2 b3 and so on will be always less than equals to 1 by b1, and which is always less than equals to 1, right? So if this will be, this will means this will be here, then if you divide by mod x both side, so what you will get is less than equals to zero point 0.5 time beta to the power minus n. So this 1 by point b1 b2 and so on will be less than equals to here b beta, right? This is here, right? Beta to the power minus 1, right? So this is going to be give you the relative error for the with respect to the rounding. Okay, so this will be here, will give you the rounding error, fine. So the rounding that relative error, okay, will be given by that. Okay, so now instead of rounding, if you are going with chopping, so there is no second part, only chopping. In the chopping case you have x minus, only x minus. So similarly you can find absolute error, and you can also find the relative error. Okay, so in chopping also you can see these are going to be given, these are the absolute error, and this is the relative error, right? Okay. Okay, now the next very important error is truncation error, or so-called discretization error. So it, as the statement is clear, it occurs when the infinite process is replaced by a finite process. So what process you are aware about so far is so-called infinite process is this in mathematical term is uh, Taylor series, right? Taylor series, right? Okay, so for example you have exponential here, e power x is 1 plus x square by 2 factorial plus x cube by 3 factorial plus and so on. So this is a non-ending series, it's an infinite series. Okay, so but machine will not accept dot dot dot. Machine will require somewhere to stop here, x to the power, let's say n by n factorial. Okay, so what is the value of n? That also you have to decide. And what will be remaining part here, that is an error. So this is called truncation error or discretization error. This type of errors are called truncation error or discretization errors, right? Okay, this is one example, right? So so it's fine. So the Taylor series expansion about the point C for f of x is given by the following. So if you look at carefully what the Taylor series expansion is doing, okay, about the point C for f of x. So here you are representing f of x, in terms of a series with n plus 1 number of terms. This first part having n plus 1 number of terms, and the second part is one term. So total are n plus 2 number of terms. Okay, the first part is called the first part is called this first part is called the polynomial approximation. Polynomial approximation. Okay, and the second part is called the error term. Error term. And this is actually the so if you see the error term here, what it is form of in form of n plus 1th derivative. So if you look at the representation of function in terms of series here, and so what you are observing is the function has some assumptions that you are able to differentiate n number of time, not in the n number of time, n plus 1 number of time, means up to nth derivative it is differentiable, and you require to apply mean value theorem n plus 1th derivative is at least continuous. Okay, so that it is called that Lagrange's mean value theorem. So this from there, this an application will give you this error term as in the following form, right? In the following form. Okay. Now, what other observation here is what you have learned also. If you somehow you are able to show that this, if I talk about analysis part, okay, reanalysis part. So if I talk about here, I means like error term tending to 0 as n tends to infinity, then you will actually write this instead of this instead of plus en plus 1, you are allowed to write dot 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 dot, means in terms of infinitely many terms. Okay, for example, sin x, cos x, a power x, you have seen that infinite Taylor series exist. Okay, so here also other important thing is that that point, this z lies between c and x. So c may be left on the x or c may be right on the x, we don't know. Further, if you have this c value is 0, if c equals to 0, we call this as Maclaurin series. Okay, so this Maclaurin series is a special case of Taylor series, right? Now, yeah, fine. So that this is here. So next we are going to learn by exploring some examples on Taylor series, how to approximate a function in terms of polynomial, and how will you control the error term. We will see in the next lecture, right? Thank you.